Alright, starting chapter 5, probability and random variables. Before we begin with the individual sections, we'll just start off with a brief discussion of probability. Sometimes it's said that probability is the science of uncertainty. And this is important for inferential statistics, because we need to know the chance we will be correct when we make estimates based on random samples. So, because when we do random samples, there's random variation in there, we're not sure exactly what answers we're going to get. There's some uncertainty in that, so we want to be able to study that to have a better sense of how much uncertainty there is in our answers. So before we get to doing that inferential statistics in later chapters, we're going to go ahead and look at several examples and rules involving probability as we run through the chapter. So starting with section 5.1, classical probability and notation. So we're going to go ahead and jump in and do some probability questions, even though we don't have a definition yet, just thinking about how probability works, and then we'll formally define it down below. So first example, let's flip a fair coin. What is the probability of heads? So fair coin meaning that heads and tails are equally likely, and in that case there's two sides on the coin. One of those is heads, so the probability of heads is 1/2. And then what we would typically do with the fraction we think of for a probability is convert that to a decimal, like 0.50. And then when we interpret that for somebody, we would usually say something like there's a 50% chance that the coin would come up heads. So 3 different versions of probability there. We have the fraction, which is the way we think about our answer, the decimal, which is the way we tend to write it, and the percentage, which is the way we tend to say it. So moving on to another example. If you roll a balanced die, what's the probability of a 3? So a balanced die is one where all 6 sides are equally likely to be the one that shows. Assuming it's a standard die, there would be one side that's a 3. So I would say that probability is 1/6. And if I divide 1 by 6 on my calculator, I get 0.1667 roughly. And moving the decimal over, I could say there's a 16.67% chance that if you roll a balanced die that you'll get a 3. Now when we look at a question like what is the probability that it will rain next Sunday, I'd have to admit that on that one I don't actually know the answer. Some answers that I often get from students are things like 1/2, and when I push them on that they say because it's either going to rain or not rain. But if you think about that, then that means there's a 1/2 chance you'll be bitten by a rattlesnake today, because that'll either happen or not happen. So luckily for us, it's not the case that every probability that will either happen or not happen is 1/2, or otherwise most of us would die because of all these dangerous things, which fortunately have much lower probabilities. But the reason I can't give you the answer to what is the probability of rain next Sunday is that it's a different kind of probability. It's not one where the possibilities are equally likely. Rain and not rain are not equally likely on any given Sunday, so I can't just go 1 out of 2 for that. So that one doesn't fall into what we call classical probability, so that's why we can't answer it, but the other ones do. The 2 sides of the coin are equally likely if it's fair. The 6 sides of the die are equally likely if it's balanced. So those fall into classical probability, also known as the equal likelihood model. And that applies to situations where each simple outcome is equally likely to occur. And a simple outcome is one that can only occur one way. So a quick example of simple outcome. When you talk about rolling a die, a 3 is a simple outcome because there's only one 3 on a standard die, but rolling an even number is not a simple outcome because there's 3 even numbers, the 2, the 4, and the 6. So for it to be a simple outcome, there can only be one way for that to happen. Alright, so let's go ahead and take a look at another example and practice those ideas. So a jar contains a total of 884 marbles, made up of a mixture of red, white, and blue. The frequencies for the colors are shown in the table below. suppose one marble is selected at random, determine the probability that the marble selected is, and they want white. So I'll put some probability notation on that. I'll put just like a P of W there. So the probability of, and I'll let that W stand for a white marble. And then I would think about what my denominator would be first. Sometimes people would say 3 because there's red, white, and blue marbles in the jar. But it doesn't say I'm going to randomly select a color. I'm going to randomly select a marble. And the colors are not equally likely because there's different counts. But the marbles, if I randomly choose, are equally likely. So the denominator would be 884. And if you're counting marbles on the bottom, then on a probability you would be counting marbles on the top as well. And how many white marbles in this jar? 289. So that would be our probability of a white marble. We'd also want to go to a decimal on that too, but I'll go ahead and do that for all these in just a moment. Let's calculate the other ones out. The probability that it's not a blue marble. So I'll put the probability of not blue. So there's two ways that you can do this that are both equally likely or equally fine. A lot of people would think about, all right, if it's not blue, what is it? And that would be red or white. So they would take 351 and add on the 289 and divide that by 884. But I'm claiming that it would be equally good to take the 884 marbles and just subtract out the ones that are blue, 244, and that either of those should give us a good answer for that one. And I'm going to further argue that if that's what you thought of when I first read the question, that you're actually in a little better position than somebody who thought of the addition. These are both the same amount of work, and they both give the same answer, so either is fine, but there will be times where this is faster. Imagine our marble jar had 27 just different colors of marbles in it. What would be better, to add up the 26 we don't want, or that we do want, or just subtract away the blue ones that we don't? Right? Pretty clear the subtraction would be better in that case. So it's a good thing to think of. You can add what you want or subtract what you don't want. And then finally, the probability of a purple marble. Probability of purple. And you look up there, there are no purple marbles, so we would say 0 out of 884, which simplifies down to 0. Alright, so that's known as an impossible event, something that cannot happen. So just bringing in the calculator real quick and calculating those probabilities. 289 over 884 is 0.3269. Standard is to round probabilities to 4 decimals, just like all other things we interpret as a percentage. And then let's look at the two versions of the next one. We get 0.72, it's a 39, but followed by the 8, so 0.7240 for this one. And notice that if I do it the other way, 884 minus 244 over 884, I get the same answer. So either one of those is fine, but going the subtraction way does have advantages sometimes. Alright, so on all those examples where we were calculating probability, we were using this rule even though we hadn't mentioned it yet. So the probability of an event has this shorthand of P of E, and it's F over N, starting with the denominator, where N is the total number of possible simple outcomes. And then F is the number of ways the event can occur. And just like I listed the N first and the F second here, when you're doing probability, especially if it's at all challenging, starting with the denominator is usually a good idea. Now, we've seen this sort of formula before, this F over N, when we were calculating population relative frequencies. And it turns out that when somebody asks you to calculate a probability, that is the exact same math calculation as calculating a population relative frequency. So in that sense, it's not new. Now, numerically, these are equal, but they don't mean the same thing. So just a quick example of that. If I think of this as a relative frequency calculation, I would say that in this jar, 32.69% of the marbles are white. But if I think of it as a probability, then I would say if you randomly select a marble from this jar, there's a 32.69% chance that you'll get a white marble. So same number, same calculation, but a different interpretation. And by the way, if you calculate the sample relative frequency for an event, you're not getting the exact probability, you're getting an approximation of the probability. So an example of that is I might toss a coin 100 times, and if I get 52 heads, that'd be 52% heads, but I wouldn't say that's the probability of heads for that coin. I would just say it's an approximation of that probability, and it's not going to be perfect. So if you have a sample relative frequency, it'll probably be close to what the real probability is, but typically it would not be the same. And the bigger your random sample was, the better approximation that relative frequency would be for the probability, and we'll take advantage of that in later chapters. Alright, a quick thing to note about probability. The probability of an event is always between 0 and 1, and that's inclusive, meaning that a probability can be 0, it can be that low, or it can be as high as 1, or anything in between. A little easier to see that in notation. So the probability of an event E is always between 0 and 1 and inclusive, so we have less than or equals rather than less than. So let me give you a question here that's a little bit challenging for most people when they haven't done probability before. Consider rolling 2 fair dice and find the probability the sum of those 2 dice is 7, or that the probability that the sum is greater than 8. So just focusing on that first question, take a minute, maybe pause the video and try and think about that. This is a tricky question for most people, and I think it's good for you to think about it before you see the answer. So after you've thought about that a little bit, whether you think you have an answer or you get stuck, go ahead and restart the video and see my explanation on that. Alright, so this is a difficult enough question that I think to answer it, we really need to be able to visualize what's going on. So I'm going to make a table here to list all of the simple outcomes to this experiment, and I'm going to use a little color to help avoid some confusions that happen here. So I'm going to pretend one of the dice is green, and so I'm going to number that one 1, 2, 3, 4, 5, 6 to list the different things that could show up on that die, and I'll do it with that color. And then I'll pretend the other die is purple. So here's our 1, 2, 3, 4, 5, 6 from the purple die. So what we want to think about are all the different sums that you can get and all the different ways that you can end up getting those sums. So suppose that on the purple die I roll a 1, then the sum of the 2 dice could be as low as 2 or as high as 7, depending on what happens on the green die. And then of course we have the integers in between as well. And if you roll a 2 on the purple die, then if it's 1 on the green, that sum would be 3. And then looking at the other possibilities with the green dice, we get 4, 5, 6, 7, and 8. If you roll a 3 on the purple, lowest could be a 4 if it's teamed up with a 1, but 3 plus 6 would be 9. And then we have the other possibilities in between. And we keep going like that, so this would be 5, 6, 7, 8, 9, 10, and 6, 7, 8, 9, 10, 11, and 7, 8, 9, 10, 11, and 12. So when I do that, that lists all the possibilities, and just to make sure this is clear, I was starting to use a pattern at the end. So this is a 10, not because it's after 9 and before 11, but because it was the 6 on the purple die together with the 4 on the green die, so 6 plus 4 is 10. So that's the way we're making that chart. And now if we start looking at the questions that we were asked, what's the probability the sum is 7? There are 6 ways right here that you can get that 7 out of 36 different possibilities. So the answer there is 6 out of 36, which is approximately 0.1667 or 16.67%. And if you figured that out without making that chart, that's pretty impressive. But I think on this problem, if you want the questions to be easier, you want to be able to visualize everything that's possible, and making this chart is a way to do that. Once we have the chart, we can answer other questions fairly quickly. What's the probability that the sum is greater than 8? So let's see, strictly greater than 8, that would be all of these numbers in this little triangle right here. And if you count through those, we've got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So that's 10 out of 36 of the possible sums produce numbers that are bigger than 8. And if we just bring in the calculator real quick on that, we have 10 out of 36, 0.27 repeating. So 0.2778 would be our answer there. So that just illustrates an important idea that if you're having a hard time thinking of what's possible on a probability question, then if it's in a reasonable amount of work to show everything that's possible, you should do that, and it'll make it much more likely that you'll get correct answers. Another thing that's common when I ask about that question in class and have people just think about it, and maybe this happened to you if you paused the video and thought about it, a lot of people for their denominator will get 12 because they're thinking 6 numbers on one die plus 6 on the other gives 12 possibilities altogether. But we can see it worked out to be 36 possibilities. 6 by 6 gave us 6 times 6, 36 possibilities, instead of 6 plus 6, 12 possibilities. And that is an illustration of what we call the fundamental rule of counting. It states that if there's X simple outcomes for one experiment, like a purple die, and Y simple outcomes for a second experiment, like a green die, then there are X times Y simple outcomes when the experiments are combined. So it's a multiplication of possibilities instead of addition. All right, so let's go ahead and move on to the meaning of probability. So one of the things we want to keep in mind whenever we do probability is that it represents the long-term relative frequency of an event. So if we had a coin that was fair, it should come up heads 50% of the time. And this is just illustrating run of that, doing the experiment and keeping track of it. So here we're counting how many times we've tossed the coin. Here we're looking at what the proportion of heads has been as we went along. So maybe at first we got a tail, so we were at 0. And then we got heads. Well, I guess on this we probably got heads first, so 100% heads. And then it's kind of bouncing around as the number of heads and tails we get is changing. But what should always happen on this is at first there'll be kind of chaos and it'll be unpredictable what your percentage will be. But whatever the true probability is, in this case 50%, your long-term proportion should be approaching that. So when we say that it's 50% for heads, that doesn't mean if you toss the coin 10 times you'll get 5 heads. You might, but that's not very many tosses, so it'll probably just be somewhere around 50% instead of necessarily exactly there. But if you toss it a bunch of times, 100 or better yet 1,000 or 1,000,000, then your proportion of heads will get really close to that 0.5. Because the random variation starts to squeeze out of that, and we saw that a bit way back in chapter 1. All right, a few definitions that we've been talking about in these examples. I was referring to the sample space. That's the collection of all possible simple outcomes of an experiment. So looking back up here at the die example, when we were doing the roll of the 2 dice, it was useful to see all the different simple outcomes, so I would say that I was showing myself the sample space to make that easier. So anytime you're looking at everything that can happen, that's the sample space. An event is a collection of outcomes. That's any subset of that sample space. And we often let a single capital letter represent an event. So you saw that with the P of E here, and I did P of W when we were talking about marbles from the jar. So those are things that happen as well. Continuing on with section 5.1, we just mentioned that sometimes a capital letter is used to represent an event, and we talked about sample space and events. And now we're going to look at Venn diagrams. A Venn diagram is used to illustrate sample spaces and events within them. When you're doing a Venn diagram, the sample space is represented by the rectangle, and the events are shown as disks inside of the rectangle. And when you talk about this sort of Venn diagram situation, it's a given that you're going to land inside the box. Remember, the sample space is the set of all things that are possible, so we're representing all the possibilities with the box. but only some of those things meet our event, and we show them inside with the disk. So a Venn diagram can be used to illustrate a basic probability event like that, but it can also be useful to illustrate new definitions of probability. And we're going to look at one of those right now. That's the complement of E, or not E, and that's the event that E does not occur. So if you thought about that one, where would we shade if we wanted to say that event not E happened? And we know we have to land in the box, but E didn't happen, so we're not in the circle, so we would shade everything that's in the box, but not inside of the circle or disk for E. So not E would look something like this, shading all possibilities except for those that are inside of the disk for E, but staying inside of the box at the same time. Alright, so that's a little bit with the basics of Venn diagrams. We'll use these again later to illustrate some more complicated probability ideas. Let's go ahead and practice this new definition of complement and some more basic probabilities by moving to an example with a deck of cards. So consider a deck of 52 cards. Our experiment is going to be select one card at random and consider the events listed below, and then find the probabilities listed below that. So the events that we're going to be working with is A, the card is a jack of spades, B, the card is a jack, C, the card is a spade, and D, the card is a face card. And then they want us to do probabilities. So as we go through to do these, the probability of event A, the card is a jack of spades. Since we're selecting a card out of a standard deck of 52, our denominator would be 52, and then the numerator would be the number of ways that A could occur. So we need to think about how many jack of spades are there in a deck of cards. So in a standard deck of cards, there's going to be only one card if you specify the denomination, which would be the jack, and the suit, which would be the spade. So if you say the denomination jack and the suit spade, that's going to narrow it down to a single card. So that's going to be just 1 out of 52. And I'll go to a decimal for that in a moment, but let's go ahead and get all our fractions done first, and then we'll bring in the calculator. For the probability of event B, we want the card as a jack. And again, we're choosing out of 52 cards. And out of those 52 cards, how many of them are jacks? Well, when you just say jack but you don't say the suit, then it could be any suit. So we would count the jack of spades, but we'd also count other jacks like the jack of diamonds as well. And it turns out that if you mention a denomination but not a suit, that always gives you 4 cards. And that's true whether you're talking about jacks or 8s or queens or some other card. If you just say the denomination only but not the suit, there will always be 4 cards that meet that description. And by the way, for those of you that maybe are not familiar with a standard deck of playing cards, there is a brief description of those and a photo of all the cards so you know what's there in the book. And you don't need to memorize all that stuff. You can reference that page whenever you need it for homework, and I won't ask questions that require knowledge of what's in a deck of cards on the test, so you don't have to worry about that. Alright, so we've got those two done. Again, we'll come back and do the calculator part in a moment. Let's move on to part C. The probability of C, the card is a spade. So again, choosing the card out of 52 from the deck, so our denominator is 52. And when we start mentioning just a suit only, then we don't care what the denomination is. So we'd want that one because it's a spade, and we'd want this one because it's a spade as well. And it turns out, if you were to look at that chart, or if you know a deck of cards, once a suit has been specified, there's going to be 13 of those. So this would be 13 out of 52, which happens to be 1/4, so that's going to be 0.25 exactly. You don't need the calculator for that one. And then let's see, the probability of D, the card is a face card. So we'd have 52 cards for our denominator, and then we'd want to count all face cards. And there's a little bit of controversy for this. So face cards are cards that have the face of a character on them. So the jack has a face on it, the queen has a face on it, the king has a face on it. We wouldn't count a card like an 8 because there's no face, it's just the number 8 and then 8 clubs showing rather than a character. It's a common misconception that an ace would be a face card as well, but if you look at the ace also does not have a face on it, it just has one spade shown in the middle. as opposed to the 8 clubs we saw a moment ago. So jacks, queens, and kings are all face cards, and we mentioned before there's 4 of each kind, so there's 4 jacks, 4 queens, 4 kings. So this would be 4 plus 4 plus 4 plus 4, or 12 out of 52, and we'll go to a decimal on that one in a moment as well. And let's go ahead and look at the final one before we bring in the calculator. So the probability of not C, so the card is not a spade. So the way I would do that one is I would look back up here and say, okay, when we were asked how many things were C, we knew there were 13 of them that were C. So that means everything else except for those 13 would meet what we want. So I'm taking the whole deck of cards, I'm subtracting out the spades because it says we don't want those. And so 52 minus 13, 52 cards minus the 13 spades leaves everything that's not a spade, which it turns out is 3/4 of the deck, or 0.75. And then just bring it in the calculator to get the decimals for the rest of those. 1 over 52, 0.0192, 4 over 52, 0.0769, and then finally over here the 12 out of 52 would be 0.2308. On every one of these I am rounding to 4 decimal places, so I'm looking at the 5th, and in this case that was a 6, so I rounded that 7 up to an 8. Alright.